Hello, and welcome to the CFE Media and Technology Virtual Training Week education session, How to Apply Direct Drive in Linear Servo Technology. I'm your moderator, Amara Razgis, with CFE Media and Technology. In keeping with our CEP policy, please take some time to read the quality assurance slide. So this session is designed for technicians and engineers who want to understand how to improve their work with direct drive and linear servo technology. Matt, would you give us a brief overview of what this session covers?
Yeah, this session is divided into two parts, and the first part is about direct drive motors, and we'll look at some applications for those and just what are some pros and cons. And the second part, we'll do something similar with linear motor stages, comparing them with ball screws and belts, and looking at how they're made, and just looking at applications, and hoping that you'll get some good information from this.
Right, and here's a list of the learning objectives. Matt, did you want to run through anything here?
Yeah, for both the direct drive motor and linear motor, we'll just look at the basic features and properties, and then go on to comparing the performance metrics for both linear motors and direct drive motors. And we want to look at different applications for each of these technologies as well.
All right, well, for a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within this session, click on the left panel labeled Notes to do so. The question and answer portion will begin in about 45 minutes, and Zoom login details are on the left side of your screen. You can obtain continuing education credits by passing an exam at the end of this course. You do have to get 8 out of 10 questions correct to get that exam credit. Here is some information about obtaining approved PDHs for today's session. All right, well, I am excited to introduce our two speakers. Brian Knight is a product marketing manager at Yaskawa for the linear and direct drive motors, Sigma Track 2 and Compass product lines. He earned his bachelor's in computer engineering from Georgia Tech and has more than 20 years of experience in motion control and industrial automation. Brian will join us shortly for the Q&A session. With a degree in electrical engineering from the University of Wisconsin-Madison, Matt Pelletier has been with Yaskawa America since 1999. Matt has worked extensively with product engineering to develop interactive hands-on training for servo tuning, IEC 61131, PLC Open, and advanced programming workshops for rotary knife, PAC-ML, robots, and conveyor tracking. Matt will be walking us through these topics and also joining us for the Q&A.
In this video, I'll explain the components of a linear motor stage and compare it to other technologies. Hi, I'm Matt Pelletier. It is beneficial to know when and how to apply linear motor technology. This requires that you know the components that comprise not only a linear stage, but the components that are used to make other linear actuators, such as ball screws, belts, and rack and pinion. I'll compare each technology using a few key metrics. The advantages and limitations of each mechanism are crucial when deciding how to apply the technology. By the end of this video, I expect you'll be able to more readily identify linear motor applications that may otherwise have been solved less effectively with a different mechanism. I'll start with a summary of what I mean by a linear motor stage, using Yaskawa's Sigma Track 2 as an example. The distinguishing feature of a linear motor is that the load moves without any mechanical power conversion. The linear force generated by the motor coil is directly connected to the load. Let's examine the construction of the SigmaTrack 2 linear stage using this 3D model. In a linear motor, the motor coil propels itself along the magnet track. The motor coil is attached to the carriage, sometimes called a slide, and the load is bolted directly to the carriage. The carriage is held in place by linear bearings with rails secured to the base. The linear bearings are the only point of mechanical contact and frictional wear. This simple fact results in huge performance benefits for the SigmaTrack 2 linear stage, or any linear stage for that matter. There is a very small air gap between the motor coil and magnet track, and the position of the carriage is reported to the control system through a linear encoder. The encoder has two parts: the scale mounted to the base and the moving reed head. Other parts of a typical linear motor stage are the cable management system and end stops. Now let's consider a few competing mechanical technologies, starting with a typical ball screw. These also have a carriage that moves on linear bearings and rails, but the force to move it is transmitted through a nut from a rotating screw. This nut is typically comprised of a system of enclosed recirculating ball bearings, which minimize friction. The screw is, of course, driven by a rotary motor, and the encoder in the motor provides position feedback to the control system. The screw is held in place with bearings at each end and connects to the motor through a flexible coupling. The ball screw is the standard go-to actuator for a wide variety of applications. Similarly, a belt actuator also has a carriage with linear bearings moving on rails. This carriage is driven by direct connection to a timing belt riding on two pulleys. The pulleys are held in place with bearings and connect to the motor with a flexible coupling. The encoder on the motor provides position feedback to the control system. A rack and pinion system is typically comprised of a motor that drives a pinion, moving itself along a fixed rack like a train on a track. The motor is mounted to the carriage, driving the pinion through a gear reduction to move the entire assembly. Now let's look at how each of these technologies compare in metrics such as initial cost, speed and acceleration, and other factors listed in this table. I'll define each of these metrics and then discuss the strengths and weaknesses of each technology. Please bear in mind that this is not a strict and absolute evaluation, but represents general industry trends. Let's start with the bottom line, initial cost. As we'll see, the linear motor generally has the highest overall performance. It goes to reason, therefore, that the initial cost is also generally higher than other technologies. Ball screws are significantly less expensive than linear motors, but they are more expensive than belt actuators, which tend toward the low end of the cost spectrum. Rack and pinion is a little tough to compare. These tend to be used in physically large systems with much larger and heavier payloads. The cost of a rack and pinion is far lower at that scale than linear motors, ball screws, and belts. But at a smaller scale, that advantage is often less distinguishable. How about speed and acceleration capability? Motion control systems have the need for speed. Faster, better, and more means a quick return on your investment. The linear motor can accelerate quickly to reach high speeds, typically around 5 meters per second. It is the performance champion for the mechanism with both high speed and acceleration. Screw-driven actuators can have strong acceleration, but above the critical speed, a screw will oscillate. This critical RPM design limitation is dependent on the diameter and length of the screw. The screw lead can be designed to move further for every turn. This increases the linear speed for the same motor RPM, but it also means more motor torque is required to move the same load. The result is that a larger and more expensive motor may be required to move at fast speeds. And occasionally these constraints have a snowball effect, resulting in a very oversized or even impossible solution. Belts can also be fast, about the same as linear motors, but as we'll see later, they have nowhere near the same precision. Rack and pinion systems can reach very high speeds, higher even than linear motors, but they typically don't accelerate quickly since they are designed to move large and heavy loads for longer distances. That brings us to length. The large systems driven by rack and pinion can be quite long, and it is cost-effective to increase the length with additional rack segments with little impact on performance. Linear motors can also be used in applications with long stroke, but the cost of magnet track and absolute encoder tape is significant. Performance, however, is unaffected by overall length. Ball screw length is limited once again by the critical speed of the screw. Longer screws begin to oscillate at a lower RPM and negatively impact tuning by lowering resonant frequencies. We'll discuss this more later. A larger screw diameter helps achieve usable speeds, but this means large motors are required to drive the longer screws, even with a small load, unless the speed is very slow. Belt drive designs are easily lengthened with minimal increase in cost. However, the effect of belt stretch becomes proportionally worse, resulting in reduced accuracy and repeatability. And like the ball screw, with increased length comes decreased stiffness and the problem of lower resonant frequencies. Horizontally oriented motion is the most common, but vertical or inclined axes are required in many applications. This means the force of gravity is constantly pushing the load down. This force must be overcome by the motor while the axis moves or holds position. When the machine powers off, a braking system can prevent the vertical axis from falling. Rotary brakes are commonly found in servomotor designs to lock the motor shaft when powered down. This makes the ball screw or belt an excellent choice for vertical loads. A vertical rack and pinion also works well for the same reasons. Linear motors are a bit more complex with vertical loads. A counterbalance or linear holding brake should always be used. A linear holding brake may be mounted externally to brake against the rail. Machine rigidity or stiffness and its inverse, compliance, is important to understand. Every mechanically connected element has a level of rigidity, a spring constant. This rigidity, along with the mass of each element, defines the natural frequencies of oscillation for the system. If these frequencies are too low, the release of energy can cause a significant disturbance to the motor. This interferes with the control system algorithms that position the load. Belt drive systems generally have the lowest rigidity and therefore the lowest natural frequencies. The belt is like a spring, and there are natural frequencies between the carriage and the pulleys. Another loss of rigidity occurs between the drive pulley and the motor coupling. As the motor begins to turn, first the coupling deflects according to the spring constant, then the belt deflects, before the load finally moves. The rigidity is further complicated since it depends on the position of the carriage and resulting length of belt in direction of the force exerted through the pulley. Ball screws have a much higher rigidity, but the same principles apply. The motor turns the coupling, which deflects, which turns the screw, which also deflects to some extent. Long, thin screws will have lower rigidity than short, wide ones. Rack and pinion is a little different. These maintain a constant and relatively high rigidity at the point of mechanical connection, regardless of the load position. But oscillations are likely to originate within the load itself if it is large and complex. But the most rigid of all these actuator technologies is the linear motor. There is no coupling or mechanical linkage to deflect. The load is connected directly to the motor through the carriage. If there are any frequencies of oscillation, they will come from the load itself and not from the mechanical system. So you see how rigidity and resonant frequency are related to load mass. This is summarized in a key performance metric called the load-to-motor inertia ratio. Servo systems are commonly sized for a load-to-motor inertia ratio less than 10:1 for acceptable control of the load by the motor through the flexible coupling. However, this ratio is of no importance in a linear stage because the motor is directly coupled to the load. Think of the load on the linear motor as nothing more than an extension of the motor itself. A linear motor has no coupling to reduce the rigidity of the system. Load mass, nevertheless, is important for linear motors as it limits the acceleration and deceleration rate according to Newton's law. It also affects bearing life. Low friction also means that nearly all the power to stop a moving load must be supplied by the electronic drive system, which can also limit the maximum load. The clear winner on moving heavy loads is the rack and pinion. These are often used on large gantry systems. Ball screws can also be sized to move very heavy loads, commonly applied in applications with moderate length and speed requirements. However, the inertia ratio and low resonant frequencies associated with heavy loads tend to limit the application. Belt mechanisms tend to have lower practical weight limits, as do linear motors. Acceleration and therefore top speed can be limited with heavy loads. Performance criteria and load mass are among the most important elements in mechanical system selection, so it is fundamental to understand these well. The performance of linear actuators can suffer from an effect called backlash. This is lost motion when the mechanism reverses. The ball screw has a level of backlash between the nut and screw. This can be reduced with preload, but preload causes the nut to wear out faster. For the belt system, backlash occurs between the teeth of the belt and pulley. The same can occur between the teeth of the rack and pinion. Manufacturers have developed ways to reduce the backlash in actuator technologies and electronically compensate for it in the control system. But there is always some level of backlash, and it tends to get worse as the mechanism wears. It means that the position of the load once again cannot be exactly determined by the position of the motor encoder, and it can also lead to tuning instability and noisy operation as the load effectively disconnects from the motor for a short time upon reversal. The linear motor is the only mechanism that can truly claim zero backlash. Position feedback is measured with a linear scale, with the reed head, carriage, and load bolted together as one piece. Rigidity, load mass, inertia ratio, and backlash are all interrelated factors that worsen the position settling time of a mechanism. Position settling time is the time delay between the end of the commanded move and when the mechanism actually stops. Reducing this delay is especially important for applications with many short moves. Waiting for the machine to stop can represent a significant fraction of the cycle time. The settling time in a linear motor can often be reduced to zero with good tuning due to its high rigidity and zero backlash, although it may be necessary to mitigate vibrations originating in the load itself. Achievable settling times for the ball screw and belt generally follow the level of mechanical rigidity and backlash, with screws generally outperforming belts. The same goes for rack and pinion, although fast moves and low settling time are typically not the focus with these larger machines. Remember that the position of these mechanisms is measured through the encoder of the rotary servo motor. The encoder may indicate that the load has settled with a low settling time, but what that really means is that the encoder has stopped moving. The load may still be in motion and not yet settled or experiencing vibration and oscillation. Rigidity and backlash interferes with the measurement of settling time through the encoder of a rotary servo motor. However, In the linear motor, the encoder is fixed to the load itself, reporting the true settling time of the load. Backlash and rigidity also contribute to a mechanism's positioning accuracy and repeatability. Accuracy is a measure of the deviation from the ideal, in this case position. If the machine is commanded to move 4 millimeters, does it move exactly 4.00000 millimeters? Or if you were to measure it externally, did it only move 3.999? What's often more important is repeatability, also called precision. Because if the machine can move to 3.999 repeatedly when you command 4.0, then simply adjust the command until it does repeatably move to the required position. The control system measures position at the encoder. Rigidity and backlash add an element of uncertainty to those measurements. Additionally, the manufacturing process of a belt, ball screw, or rack and pinion will affect the accuracy and repeatability. Only the linear motor, by natural design, measures the load directly and moves it without the backlash and compliance problems that can plague mechanical actuators. You may have been thinking, why not compensate for the shortcomings of ball screws, belts, and rack and pinion mechanisms by adding a linear encoder? Yes, this is possible, and at Yaskawa we call it full closed loop. This allows the position loop of the rotary motor to be closed by linear encoder feedback. However, adding a linear encoder adds significant cost and complexity. The linear scale must be accurately placed. The read head clearance to the linear scale must be accurately aligned. And now you'll have a cable track for cable management of this encoder on the carriage. Most servo amplifiers don't support a second encoder input without additional hardware cost. Servo tuning will also be affected and must be completed again. In short, if the performance of an existing system must be improved, then full closed loop is a viable option. But it is generally not a significant cost savings compared to using a linear motor in the first place. Adding full closed loop will improve repeatability and accuracy, but it does not do much to improve rigidity, settling time, and wear. So ask yourself the question, will a linear encoder on a belt, ball screw, or rack and pinion really save money in the long run? There's no avoiding it. All mechanisms wear. Let's take some time to understand what part of the mechanism wears and what happens to the system performance as a result. In the linear stage, only the linear bearings wear out, but until they utterly fail, that stage will position accurately, at least in the linear direction, while pitch and yaw and roll of the carriage may deteriorate over time. Some linear bearings require lubrication, but self-lubricating linear bearings are commonly available, such as those used by SigmaTrack 2. The same applies to linear bearings on a ball screw, belt, or rack and pinion. But these mechanisms have other moving parts that wear out. The screw itself, the nut, the bearings on the screw, motor bearings, belts, rack and pinion, and gearboxes all wear out even with regular lubrication. From day one, the performance of these mechanical systems begins to decline. The backlash and stiffness get a little worse every day. Therefore, expect positioning time, accuracy, repeatability to continually degrade as time goes on. The linear motor bearings do eventually wear out, but quite gracefully by comparison. Different mechanisms are best suited for different industrial environments. Consider the magnetic field of the magnet track of a linear motor, which may attract particles. A bellows protection system will help keep particles out of the magnet track. While linear encoders don't require a clean room, they do their best in a reasonably clean environment free of excessive dust and oil. The linear scale can still work with some interference, but for very dirty environments, consider a custom linear motor with an inductive or magnetic linear encoder. The ball screw is used commonly in machine tool and other dirty environments, although the screw must be protected. Belts and rack and pinion also work well in many environments. Clean rooms are on the other side of the spectrum, where it is critical to reduce the number of microscopic particles emitted by the actuator. Linear motors can be easier to make clean room compatible. The many wear points of ball screws, belts, rack and pinion, or other mechanisms with mechanical power transmission are generally less desirable for cleanroom operation due to the number of particles ejected during operation. When selecting the right actuator for an application, consider the long-term cost and performance. There are applications with specific constraints which logically eliminate linear motors from consideration. Other applications have long been the strength of linear motors: long stroke or high speed, fast acceleration, precision and accuracy. But there's a middle ground where linear motors are often overlooked in favor of the traditional solutions like ball screws, belts, or rack and pinion. Solving these applications with linear motors can save money in the long run while providing exceptional and stable performance over the life of the machine. I hope this gives you a solid introduction or maybe review, and when you do consider a linear motor, please consider Yaskawa's SigmaTrack 2 and custom linear motor solutions. In this video, I'll introduce industrial direct drive servo motor technology and applications. I'll show you what a direct drive motor is, and then compare performance metrics to transmission-based alternatives. I'll illustrate the specifics using a few application examples and a case study. Let's get started. Here is a typical direct drive motor mounted to a steel plate. I can rotate the flange by hand when it's powered off. Now I'll turn it on and run a gentle test move. A direct drive motor is characterized by the cylindrical shape with a hole through the middle of the rotating flange. There is no motor shaft like you'd see on a standard servo motor, but the rotating part is still called the rotor, with mounting holes along the flange. The load attaches directly to the flange of the motor, hence the name direct drive motor. Even this small unit is pretty heavy, so I'll use a 3D model for the rest of this description. The part that does not move is called the stator. It's where the cables connect. The stator also has mounting holes, which bolt to the machine frame. Motors like this may also be called a torque motor or a hub motor. Direct drive motors have much higher torque than a standard servo motor and much lower speed. They trade speed for torque, with typical top speeds of just a few hundred RPMs down to only tens of RPMs with extremely high torque. The speed-torque curve of a direct drive motor is a lot like that of a servo motor with a gear reduction around 10 to 1 and up, sometimes as high as 100 to 1. These curves show the RMS and peak operation points for an application that would fit either a geared servo motor or a direct drive motor. Both motors have continuous torque up to about 28 Newton meters and peak torque up to about 50 Newton meters with a top speed just over 100 RPM. And here are the motors shown to scale. The direct drive motor is obviously much larger with a wide mounting flange. Both motors can solve this application, but even the best gearbox adds a level of compliance and backlash. For this reason, the direct drive motor will accomplish the task with higher accuracy, better repeatability, and lower settling time. I'll explain more about this in a few minutes. Direct drive motor applications have relatively low speed, and the mechanism is designed for flange mount instead of shaft mount. The most common application is a rotary table or rotary indexer. Another good application is to drive the spool in a winding application, or rolls for printing or cutting. Joints for robotic mechanisms can also benefit from the performance and compact size of a direct drive motor. Rotary positioning of grippers for pick and place or antennas, telescopes, rotary part fabrication, and laser positioning are also applications where a direct drive motor can offer superior performance. Direct drive motors are generally not used on linear mechanisms. The linear direct drive equivalent is a linear motor, which directly drives the load to avoid backlash and compliance found in mechanisms such as a belt, ball screw, or rack and pinion. Like a standard servo motor, the rotor of a direct drive motor is built from an iron structure with an assembly of permanent magnets. The coils in the stator produce a moving magnetic field, which applies torque in the desired direction. Position feedback to the control system is provided through a rotary encoder. Two basic rotor design layouts exist, inner rotor and outer rotor. This is inner rotor with stator coils on the outside, and the opposite configuration is outer rotor with the stator coils on the inside. The inner rotor configuration is capable of the highest acceleration for a given motor size. Outer rotor means the motor has a higher moment of inertia, better suited to control high inertia loads. Two basic stator designs also exist: iron core and coreless. The stator coils can be wrapped around an iron core, which increases the magnetic field strength in the stator, resulting in higher torque in a smaller motor. Coreless means there is no iron in the coils. While the torque for a given motor size is lower, coreless provides the most accurate speed control without the cogging torque component of torque ripple. It makes sense to understand the direct drive motor alternatives for a given rotary application. I'll use a few 3D models to represent these machines. The most popular is to use a planetary gear or other gear technology to reduce the speed and increase torque. A similar effect can be achieved using a system of belts and pulleys, and sometimes both are used together. Now let's look a little deeper into the details behind the direct drive performance advantage for rotary applications compared to a gear or belt mechanism with similar torque and speed characteristics. We'll look at cost, torque, speed, rigidity, backlash, and others listed here. I'll define each of these metrics and then discuss the strengths and weaknesses of each technology. Please bear in mind that this is not a strict and absolute evaluation, but represents general industry trends. I'll start with the bottom line, initial cost. A belt and pulley transmission costs significantly less than a gearbox, but the maximum reduction is about 3 to 1. This means that an application with low speed and high torque will require a significantly larger and more expensive servo motor and amplifier. The initial cost of a direct drive motor is still significantly higher than either of these transmission-based alternatives. But in addition to the motor and transmission, you have the cost of couplings and additional bearings to support the load. Integrating these components incurs a design and engineering cost, and then consider the long-term cost of performance and maintenance. For low-speed rotary applications, the direct drive solution is a simple design which may actually incur the lowest initial cost while providing the highest long-term performance. One of the most important performance characteristics is rigidity. Every mechanically connected element has a level of rigidity, a spring constant. This rigidity, along with the mass of each element, defines the natural frequencies of oscillation for the system. If these frequencies are too low, the release of energy can cause a significant disturbance to the motor. This interferes with the control system algorithms that position the load. In a belt-based transmission, a servo coupling connects the gearbox output to the rotary load. The weight of the load is supported by a ring-style bearing. The belt and pulley ratio has a practical limitation of around 3 to 1, beyond which the angle of the belt results in too little surface contact with the drive pulley. It's usually not practical to attempt to correct the situation with multiple stages or excessively long belts. Instead, the servo motor would be oversized in order to achieve the required torque for a low-speed application. Belt-based transmissions generally have the lowest rigidity and therefore the lowest, most problematic resonant frequencies. In this example, as the motor begins to turn, first the belt deflects according to its spring constant, then the coupling deflects before the load finally moves. Rigidity losses also occur due to motor couplings and long machine shafts. With a gear-driven transmission, a servo coupling connects the gearbox output to the rotary load. The weight of the load is supported again by a ring bearing. Planetary and multi-stage gearheads are generally preferred for low backlash and high rigidity, but a single-stage gear reduction is shown here just for simplicity. Gearboxes have much higher rigidity than belts, but the same principles apply. The motor turns the input gear, which deflects, which turns the output gear, which also deflects to some extent. The coupling to the load may be what deflects the most. The direct drive motor bypasses all of the transmission components, the resultant compliance, and the associated resonant frequencies. The direct drive motor is typically equipped with very large bearings for greatly increased axial and radial load capacity. That's not to say there is no resonance. Resonant frequencies can still be generated by the load itself or through any mounting plates or extensions between the motor and the load. There can even be resonance between the stator of the motor and the machine frame, just as are found on transmission-based systems. But the high rigidity of the direct drive system results in high resonant frequencies which lie outside the operational system bandwidth. Resonant frequency is also a function of load inertia and motor inertia. This is summarized in a key performance metric called the load-to-motor inertia ratio. Servo systems are commonly sized for a load-to-motor inertia ratio less than 10:1 for acceptable control of the load by the motor through the flexible coupling. Direct drive applications don't use a flexible coupling and therefore can support much higher inertia ratios. Load inertia is nevertheless important for direct drive motors as it limits the acceleration and deceleration rate according to Newton's law. It also affects bearing life. The low friction in a direct drive motor means that nearly all the power to stop a moving load must be supplied by the electronic drive system, which can also limit the maximum load. The performance of rotary drive transmissions suffer from an effect called backlash. This is lost motion when the mechanism reverses. The gearbox has a level of backlash between the drive sprocket and the output sprocket. For the belt system, backlash occurs between the teeth of the belt and pulley. Manufacturers have developed ways to reduce the backlash in drive transmissions and electronically compensate for it in the control system, but there's always some level of backlash, and it tends to get worse as the mechanism wears. The result, once again, is that the position of the load cannot be exactly determined by the position of the motor encoder, and it can also lead to tuning instability and noisy operation as the load effectively disconnects from the motor for a short time upon reversal. The direct drive motor is the only rotary drive mechanism that can truly claim zero backlash. Since the motor is directly connected to the load position measured by the motor encoder is much closer to the load itself. Rigidity, load inertia, inertia ratio, and backlash are all interrelated factors that worsen the position settling time of a mechanism. Position settling time is the delay between the end of the commanded move and when the mechanism actually stops. Reducing this delay is especially important for applications with many short moves. Waiting for the machine to stop can represent a significant fraction of the cycle time. The settling time in a direct drive motor can be significantly reduced with good tuning due to its high rigidity and zero backlash, although it may be necessary to mitigate vibrations originating in the load itself. Achievable settling times for the gearbox and belt generally follow the level of mechanical rigidity and backlash, with gearboxes generally outperforming belts. Remember that the position of these mechanisms is measured through the encoder of the rotary servo motor. The encoder may indicate that the load has settled with a low settling time, but what that really means is that the encoder has stopped moving. The load may still be in motion and not yet settled or experiencing vibration and oscillation. Rigidity and backlash in the transmission interfere with the measurement of settling time through the encoder. However, in a direct drive motor, the encoder is essentially fixed to the load itself, reporting the true settling time of the load. Backlash and rigidity also contribute to a mechanism's positioning accuracy and repeatability. Accuracy is a measure of the deviation from the ideal, in this case position. If the machine is commanded to move 90 degrees, does it move exactly 90.00000 degrees? Or if you were to measure it externally, did it only move 89.99999? What's often more important is repeatability, also called precision. Because if the machine can move 89.999 repeatably when you command 90, then simply adjust the command until it does repeatably move to the required position. The control system measures position at the encoder. Rigidity and backlash add an element of uncertainty to those measurements. Additionally, the manufacturing process of a gearbox or belt system will affect the accuracy and repeatability. Only the direct drive motor, by natural design, measures the load directly and moves it without the backlash and compliance problems found in rotary drive transmissions. You may be thinking, why not compensate for the backlash and rigidity of gearbox or belt transmissions by adding a rotary encoder to the load if the application requires it? Yes, this is possible, and at Yaskawa we call it full closed loop. Full closed loop allows the position loop of the rotary motor to be closed by an additional rotary encoder mounted directly to the load. This improves repeatability and accuracy, but does not do much to improve rigidity, settling time, and wear. Adding an external encoder like this is rarely implemented because it adds significant cost and complexity. Here's an example of a machine that takes advantage of direct drive motor technology. The laser engraves very small features onto a very small part, which is rotated precisely and rapidly by a direct drive motor. The whole assembly must be small because it is suspended on an arm which also rotates. Compact design with high accuracy and low vibration makes the direct drive motor a superior choice over gear or belt transmissions. This machine relies on high-speed rotary positioning of a gripper to handle small parts. It's easy to see the direct drive motor here on this machine and the simple mounting design. Since there was no backlash, the positioning was made repeatable on this small load with a settling time lower than 5 milliseconds. Additionally, the hollow bore design provided space for all vacuum tubes and wires to pass through the motor mount. This multi-axis robotic mechanism is called a 4-bar linkage. The direct drive motor drives the long leg, while a rotary motor drives the short leg with the shaft running through the hollow bore. It's a compact and low-profile solution for a variety of positioning applications. Rotary printing applications like this can benefit from the direct drive motor to achieve high repeatability and low backlash in order to respond to slight phase adjustments and remain synchronized with the material. Now let's look at a case study. A machine may actually be losing money due to settling time performance, and this is rarely considered during the servo motor sizing process. This effect was clearly demonstrated in a series of articles written by engineers at Yaskawa America Incorporated and published by Control Engineering. In this setup, a Yaskawa direct drive motor and a Yaskawa gear motor of similar power capacity ran the same load with the same motion profile. On the gear motor, the planetary gear was a 50-to-1 reduction, and the rated backlash was less than 5 arc minutes. The move profile required both motors to accelerate and decelerate near their peak torque rating, and with an RMS torque just below the continuous rating. Both motors were tuned until the settling time was near 50 milliseconds, as measured by the motor encoder. The graph of the result shows the motor position approaching the 45-degree mark in green. Blue shows the actual position of the motor, lagging about 50 milliseconds behind, settling to within 0.05 of a degree in a time of about 25 milliseconds. And red shows the externally mounted ring encoder position. On the direct drive motor, both encoders report essentially the same position at all times. But on the gear motor, you see the load is ahead of the encoder during the final deceleration and then oscillates at the end of the move. This low-frequency oscillation is due to the backlash and compliance of the gearbox and not oscillation of the load itself. It does not settle to within that same 0.05 of a degree until about 130 milliseconds. The motor encoder does not reveal this oscillation, so an additional delay would be required in the programming sequence to wait for it to settle out. Let's put this case study in terms of dollars and cents in a real application scenario. Consider that this machine represents an 8-station index table producing the proverbial widget. Each of these 45-degree index moves theoretically complete in 200 milliseconds with the 0.05 of a degree in-position tolerance. Then an external 2-second work process happens at each station. At the final station, one widget is produced, resulting in a revenue of 50 cents. The direct drive system completes the cycle in 2,225 milliseconds, producing revenue of $809 per hour. The gear motor takes 2,305 seconds due to longer settling time and produces $772 per hour of revenue. That difference of $37 per hour may not seem like much, but do a little more math and it's a difference of $293 in an 8-hour shift, nearly $1,500 in a 5-day week, and more than $73,000 per year. Even if each widget revenue is only 10 cents, the machine could still produce nearly $15,000 more revenue per year in the same operation time. So I hope this case study illustrates how important it is to consider the impact of achievable settling time when sizing and selecting the servo motor for the application. But that's not the end of the story. A natural part of machine ownership is wear and maintenance. In a direct drive motor, the main motor bearing is the only point of friction and wear, and these motor bearings are typically sized for extremely heavy loads. But gearboxes and belt transmissions have other moving parts that wear out, may require lubrication, or other periodic maintenance. Audible noise is also louder compared to direct drive motors. As they wear, the performance of these transmission-based mechanisms begins to decline. The backlash and stiffness get a little worse every day. Therefore, expect position settling time, accuracy, and repeatability to continually degrade as time goes on. For low-speed rotary servo applications, look closely and strongly consider direct drive motors. The upfront cost is easily offset by the increase in performance, simplicity of design, and ease of maintenance. Let me leave you with a few design considerations. First, remember that the bearing on a direct drive motor is robust and can support the weight of the entire load. No additional bearing is required, as would be when gearboxes or belt transmissions are used. This is a savings in part cost, design, engineering, and maintenance on the system as a whole. Next, the rigidity discussion so far was largely limited to the transmission components, but the rigidity of the machine itself also comes into play. The stability of any motor depends on a rigid connection from the stator to the machine base. Adapter plates and frame structural members must be as robust as possible. What may look rigid is likely to flex and deflect under the extreme torque applied by a direct drive motor. Both mounting frames and load plates can be sources of machine oscillation in any application, not just with direct drive motors. Finally, it may be tempting to consider an oversized gear motor solution to beat the initial cost of a direct drive motor with the intention to compensate for long settling time by programming a faster move. Keep in mind, however, that faster acceleration requires more torque and therefore a larger amplifier, coupling, gearbox, and possibly changes to the machine frame. And be sure not to exceed limitations on the load itself or on the parts and assemblies in motion. It is also useful to remember that while a larger motor on the same load results in lower inertia ratio, the resonant and anti-resonant frequencies will actually decrease and become more likely to cause complications with oscillation and tuning. I hope this gives you a solid introduction or review. Yaskawa does offer coreless motors and a wide selection of iron core inner rotor and outer rotor direct drive motors. So when it's time for a direct drive motor, please consider Yaskawa. Thank you for watching this video, and please go to www.yaskawa.com for more information.
Matt, that was fantastic. Now we want to take some questions from the audience. Please join me, Matt, and Brian for the Zoom Q&A session. You can find details about this on the left side of your screen. All right, well, a couple of reminders for you. More resources can be downloaded on the left side of the screen below the education sessions agenda. If you'd like to add any notes to your personal education session, click on the left panel labeled Notes to do so. And let's continue this discussion. And you can ask questions of Matt and Brian by joining us right now for the Q&A. You can find that on the left side of your screen, and you'll have to enter a new area to participate. This session is available on demand. And if you missed something or you'd like to go back to a portion, you can certainly do that in some more depth. All right, well, thank you so much for attending the education session, How to Apply Direct Drive and Linear Servo Technology. I'm your moderator, Amara Rauskas, Content Manager with CFE Media and Technology. Thank you for joining us for this education session.